Welcome back to the deep dive.
Yeah.
Today we are tackling a subject that I think a lot of us, well, we think we understand it,
Yeah, we think we do.
right? But if the massive stack of research you've brought to the table today is any indication, we are actually looking at it completely backwards.
We really are.
We are talking about the digital twin. And I'll be honest, when I hear that term, I just picture a really nice high-resolution 3D model of a car. You know, the kind spinning around on an iPad screen at a dealership.
Little shiny marketing tool.
Exactly. It feels
Yeah.
like a gimmick. But you're telling me that this view is, well, not only is it outdated, but it's missing the single biggest revolution happening in automotive engineering right now.
It is completely missing the point. If you think a digital twin is just a 3D marketing asset, you are stuck in 2015.
Okay.
What we are seeing in the strategic outlook for, say, 2024 through 2026 is a fundamental restructuring of how machines are made. The digital twin has evolved from a picture of the car into the core infrastructure of the car. It is the spine that connects the design phase, the manufacturing phase, and the driving phase.
So it's not just a reflection.
No, it is not a reflection of reality anymore. In many ways, it is becoming the reality.
That is a heavy statement.
Yeah.
Becoming the reality. Let's unpack that for a second, because the sources we have here, these strategic reports and technical white papers you shared, they keep using two phrases that honestly sound a bit like science fiction.
Virtual first and zero prototypes.
Yes. Virtual first and zero prototypes.
Yes, virtual first and zero prototypes. Now, zero prototypes sounds, frankly, it sounds dangerous to me. Are we really saying that major automakers are trying to stop building physical test cars?
That is exactly what they are doing.
That's wild.
And I get it. It sounds dangerous if you were thinking about the old way of engineering, because the traditional cycle was you design it, you build a clay model, you build a handmade prototype, you crash it into a wall.
See what broke.
Exactly. See what broke. Then you redesign it, build another one, and crash it again, which takes forever.
That loop takes years and costs hundreds of millions of dollars. The industry simply cannot afford that anymore.
Because things are moving too fast.
Right. The goal now is to verify everything. And I mean absolutely everything, from the molecular chemistry of the battery cells to the way radio waves bounce off the door handle.
You do all that inside a simulation.
Yes, inside a simulation before a single piece of metal is even cut.
So effectively, we're building the car in the matrix before we build it in the factory.
That is the perfect analogy. And to extend that matrix analogy, the car in the simulation is the master product.
The master product.
Right. The physical car that you buy and drive off the lot, that is just a physical instance, a printout, really, of the software master.
A printout.
Yeah. If the simulation says the car works, the physical car will work, provided the manufacturing is accurate.
That flips the whole script. I always assumed the physical car was the real thing and the computer model was just a sketch.
A lot of people do.
But you're saying the computer model is the source of truth. So why is this shift happening right now? Why the 2024 to 2026 window?
It is the collision of two massive forces. First, you have the software-defined vehicle, or SDV.
Right.
A modern car is not just a combustion engine with a radio anymore. It is a distributed server room on wheels.
It's basically a giant computer you sit in.
Exactly. You have millions of lines of code, dozens of computers, and complex sensors all trying to talk to each other. The complexity has absolutely exploded.
And second force.
The market is demanding speed. You used to have 5 to 7 years to develop a new car platform.
Oh, wow.
Now, with the competition from agile EV startups and Chinese manufacturers, you have maybe 2 or 3 years.
That is a massive compression.
It is. You cannot reconcile that explosion in complexity with that compression of time using physical prototypes. It is mathematically impossible.
So you have to go virtual.
The only way to solve it is to move the work into the virtual world?
Right, because if you find a bug in the code or a flaw in the dashboard design and you're relying on a physical prototype, you might be 6 months away from fixing it.
Exactly.
But in the virtual world, you just fix it in an afternoon.
Exactly. And it's not just about fixing bugs, it's about optimization. You can run 10,000 iterations of a suspension geometry in the cloud overnight.
Which you could never do physically.
You could never build 10,000 physical suspension arms to test. It would take a lifetime.
So we have a clear roadmap for today's deep dive. We are going to look at 5 specific battlegrounds where this technology is being deployed based on the research.
The 5 pillars.
Right. We aren't just talking high-level concepts today. We are going deep into batteries, HMI and autonomous driving, cybersecurity, the black magic of hardware physics, and finally, the cloud-native architecture.
If you want to understand the future of the car, you have to understand these 5 areas.
Let's start with the heart of the beast then. Section 1, batteries and propulsion. Now, as an EV driver myself, this is the one that gives me the most anxiety.
Range anxiety is real.
It is. I look at my dashboard, I see the range dropping, and I wonder, is my battery healthy? Is it degrading? Is it going to just brick itself the day after the warranty expires?
That's every EV owner's nightmare.
Exactly. So how is a digital twin helping with that?
This is one of the most exciting applications in the research. We are seeing a move toward what is called cloud edge synergy.
Cloud edge synergy. That sounds like some serious buzzword soup.
It does sound like buzzword soup, I admit.
Rah.
Let's break it down. Your car has a battery management system, or BMS, on board.
Okay.
That's the edge. It's a computer, but it's a relatively simple one. It's watching the voltage, the current, and the temperature in real time to make sure nothing explodes right now.
So it's the bodyguard. It stops immediate threats.
Correct. But it's a bodyguard with amnesia.
Amnesia.
Yeah. It doesn't have the storage or the processing power to remember what happened 3 years ago or to run complex physics simulations.
Ah, I see.
That is where the cloud comes in. The car beams its data up to the cloud, where a high-fidelity digital twin of your specific battery pack lives.
Just my battery pack.
Yes, your specific one. And this twin is running massive, heavy computational models, things like LSTM networks.
LSTM. Let me check the notes. That stands for long short-term memory, right?
Mhm.
That's an AI term.
It is. It's a type of neural network that is specifically designed to recognize patterns over time.
Over time.
A standard BMS just sees, hey, the voltage is 400.
Just a snapshot.
Right. But the LSTM model in the cloud sees the voltage is 400, but 3 weeks ago it was 400.1 under these exact temperature conditions. And 6 months ago, you supercharged it while it was freezing cold.
Wow.
It takes the entire history of the battery to predict the future.
So it's not just looking at the number right now. It's looking at the trend line and the context of how you've treated it.
Precisely. And this allows for true predictive maintenance. The sources highlight a specific, really impressive capability of predicting micro short circuits.
Micro short circuits. What are those?
These are tiny, microscopic bridges that form inside the battery cells. They're often due to dendrite growth.
Dendrite growth.
Yeah, it's basically lithium plating that grows inside the battery like stalagmites in a cave.
And those are the things that eventually touch the other side and cause a short.
Yes, and that is what leads to thermal runaway. Fire.
Oh, wow.
A standard BMS often can't see a microshort until it's too late because the voltage drop is just so subtle.
It's invisible to the local computer.
Exactly. But the cloud twin, using these complex autoencoder models, can spot the spectral signature of a microshort weeks in advance.
Weeks.
Weeks. It sees a tiny anomaly in the data that shouldn't be there based on the physics model.
That is incredible. So the car could literally tell you, hey, cell block 4 is acting funny. Come in for service 3 weeks before it actually fails or catches fire.
That is the promise of the digital twin. And it's not just safety, it's efficiency too.
How so?
The research talks about dynamic optimization. Because the cloud has the data from the entire fleet, thousands and thousands of cars, it knows how batteries degrade under every possible condition.
Right.
So it can send a custom charging strategy back down to your specific car.
Custom for me.
Yes. It might say, for this specific driver who drives mostly on highways in the Arizona heat, we need to adjust the charging curve to be 2% gentler at the top end.
And that micro adjustment adds up over time.
The data suggests it can extend battery life by 7 to 10%.
10%.
That is a massive amount of value. Think about it. If your battery lasts 10% longer, that's 2 more years of life for the vehicle.
And that is purely software.
Purely software. No hardware changes at all.
That is the absolute definition of value add. Now, staying in the powertrain for a minute, let's talk about the motor itself.
Okay.
The outline mentions something called torque ripple. And I have to admit, when I first read that in the sources, I thought of a delicious ice cream flavor.
I can see that.
But I am gathering from the physics papers that it is not delicious.
It is definitely not delicious, and it is very annoying for engineers. Torque ripple is vibration.
Vibration.
Yeah. In an electric motor, you want the power delivery to be perfectly smooth, a flat line. But because of the way magnets and copper coils work, the power is actually delivered in pulses. It ripples.
Like a stutter.
A very fast stutter. You might feel it as a subtle vibration in the steering wheel, or hear it as a high-pitched whine.
Okay, I've definitely heard that whine in some EVs.
Right. Now, traditionally, you solve this with better hardware. More expensive magnets, better insulation, tighter tolerances.
Throw money at the physical problem.
Exactly. But the industry is moving to 800-volt silicon carbide systems. These are high-performance, high-voltage beasts.
They pump a lot of juice.
A ton of juice. And the traditional control math, which is called field-oriented control, or FOC, starts to break down at these extremes.
Why does the math break down just because there's more power?
Because of nonlinear magnetic saturation.
Okay, you lost me.
Imagine a sponge. When it's dry, it soaks up water easily. That's a linear relationship. But when it's totally soaked, you can't push any more water in.
Right, it just spills over.
That's saturation. The magnets in these new motors are being pushed so hard they get soaked with magnetic flux. They stop behaving in a straight line.
Ah, I see.
But the old math assumes the sponge is always dry.
So the computer thinks the motor's doing one thing, but the physical reality is that it's doing something entirely different.
Exactly. And that mismatch between the math and the physics causes the ripple.
So how does the digital twin fix a physical magnet problem?
The solution is fascinating. They are running a mathematical twin of the motor in parallel with the real motor.
Wait, in the cloud?
No, right on the chip inside the car.
On the car's chip.
Yes. The new chips, like the NXP S32K396 mentioned in the notes, are finally powerful enough to do this locally.
Okay.
They run a real-time simulation that says, based on the physics of saturation, this is what the current should be.
It predicts the reality.
Yes. It compares that prediction to reality and corrects the electrical signal thousands of times a second to literally cancel out the ripple.
It's like noise-canceling headphones, but for the motor's torque.
That is a perfect way to visualize it. It uses a digital model of the physics to clean up the physical reality.
That's brilliant.
The result is a smoother ride and less energy wasted as heat. And it's all done through math instead of expensive materials.
Now, before we move out of the battery section, we have to touch on the digital battery passport. This brings in the regulatory angle from the research.
The European Union mandate.
Right, the EU is mandating this by 2027. What exactly is a battery passport, and how does the digital twin fit into that regulation?
The battery passport is basically a birth certificate and a medical record for every single battery pack on the road.
Okay.
The EU wants to know where the lithium came from, how much carbon was emitted to manufacture it, and what its current state of health is.
They want full traceability.
Exactly. But the digital twin takes this traceability to a granular level. We are talking about micro-measurements from the production line.
What kind of micromeasurements are we talking about here?
The system records the exact pressure used to weld the bus bars together. It records the exact amount of thermal glue applied between the cells down to the milligram.
Down to the milligram.
Yes. It even records the ambient temperature and humidity of the factory floor at the exact moment the cell was sealed.
Why on earth do we need to know the temperature of the factory floor from 5 years ago?
Because it establishes a zero baseline.
A zero baseline.
Right. If a battery fails 5 years later, engineers don't have to guess why. They can pull up the digital passport and see, oh, look, this specific batch of cells was sealed on a Tuesday when the humidity was 2% higher than normal.
And that extra humidity caused a slow degradation.
Exactly. They can trace the failure back to the absolute root cause. It turns the battery from a mysterious black box into a fully transparent history book.
So it connects the manufacturing twin on the factory floor directly to the operational twin in your driveway.
It's one continuous thread of data throughout the entire life cycle.
And that is what we mean by core infrastructure.
Exactly.
All right, let's move out of the engine room and into the driver's seat. Section 2 HMI, which is human-machine interface and autonomous driving.
This is where things get very visual.
Yes, this is where the visuals come in. I've seen some of these demos in the source material using Unreal Engine 5.
The gaming engine.
Right, which is the exact same software they use to make video games like Fortnite. It looks amazing, but I have to ask, is it just eye candy?
It creates a lot of eye candy, sure. But for the engineers building autonomous systems, the visuals are entirely secondary to the physics of the light.
The physics of the light.
When we talk about using Unreal Engine or simulation platforms like VI World Sim for autonomous driving, we aren't just trying to make a pretty picture for a presentation. We are doing physical sensor modeling.
Physical sensor modeling. So it's not just rendering what a generic camera sees, but simulating what the specific sensor detects.
Exactly. If you are training a self-driving AI, You can't just feed it a cartoon rendering of a street.
Because reality doesn't look like a cartoon.
Right. You have to feed it data that looks exactly like the raw data the car's actual sensors will generate in the real world.
So what does that involve?
That means simulating how a LiDAR laser beam bounces off a wet leather jacket versus how it bounces off a dry cotton t-shirt.
Are you serious? It gets that detailed.
It has to. It means simulating the exact lens flare on a specific camera model when the sun is low on the horizon. It means simulating the multipath reflections of a radar signal bouncing back and forth between a guardrail and a semi-truck.
That sounds incredibly computationally expensive. You're simulating the physics of individual photons and radio waves in real time.
It is massive. The computing power required is staggering. But it's absolutely necessary because of what we call the curse of rarity.
That sounds like a Pirates of the Caribbean movie title. The curse of rarity. What is it?
It is the fundamental problem of autonomous vehicle testing. The problem is that 99.9% of driving is boring and easy.
Right, staying in your lane on a sunny day.
And the AI learns that very quickly. The dangerous stuff, the edge cases, are extremely rare.
Like what?
You could physically drive a test car for 1 billion miles and never see a child drop a box of reflective marbles on the highway during a snowstorm at sunset.
Right, it's a 1 in a trillion event. But if the AI has never seen it, it might completely panic when it happens.
Exactly. You cannot physically drive enough miles in the real world to catch all these rare edge cases. It would literally take us centuries of driving.
So we use the digital twin to break the curse of rarity.
We do. We generate these nightmare scenarios in the simulator. We can make it rain mattresses on the highway.
Rain mattresses.
You can make every pedestrian jump out into traffic at the exact worst moment. Yeah. We can test the car against the impossible scenarios over and over and over again.
So you are training the brain of the car in a nightmare simulator where everything goes wrong all the time.
We are deliberately stressing it to the breaking point. And specifically, we are using this to test the handover.
The handover.
This is the most dangerous moment in level 3 automation. It's the moment when the car realizes it can't handle the situation and tells the human, you take control.
That's the scary part. If you're driving an EV with this tech, you might be checking your emails, the car's driving, and suddenly it beeps and says, your turn, while you're doing 70 miles per hour.
Precisely. And the engineering question is, how does the car communicate that urgency?
Right.
Does the seat vibrate? Do the ambient lights flash red? Does an alarm sound? And most importantly, how long does it take the human to physically react and grab the wheel?
How do you test that without risking lives?
We test this using driver-in-loop simulators.
Driver-in-loop.
We put real human test subjects in highly realistic physical cockpits. We surround them with massive screens or put them in VR headsets, and we throw these simulated edge cases at them.
So you're testing the human as much as you're testing the machine?
We are testing the interface between the two. The research mentions a staggering stat on this. Engineers can complete 80% of the HMI subjective experience sign-off before any physical molds are cut for the dashboard.
Subjective experience. That's the feeling of it, right?
It's all the stuff that's hard to measure with numbers. Is this warning chime annoying? Is that red warning light too bright for night driving? Is the touchscreen menu logic confusing when you're in a panic?
And traditionally, you wouldn't really know that until you built a physical prototype interior and sat in it.
Right, and by then it's very expensive to change. Now, you iterate that hundreds of times in the simulator with real people. By the time you pour the plastic and cut the steel for the real car, you already know the human experience is perfect.
This zero prototype concept just keeps coming back. It's not just about saving money on scrap metal. It's about perfecting the design before the metal even exists.
It's about failing fast and failing cheap. In the digital world, a crash costs $0 and hurts no one.
Speaking of crashing, let's talk about crashing the software itself. Section 3, cybersecurity.
This is a critical battleground.
You mentioned earlier that the car is a server room on wheels. Well, server rooms get hacked, and if my laptop gets hacked, I lose some data, maybe some photos. If my car gets hacked on the highway, I lose my brakes.
The stakes are infinitely higher. And as cars become more connected with V2X, which is vehicle-to-everything communication, 5G networks, over-the-air updates, the attack surface grows massively.
Because every connection is a potential door for a hacker.
Exactly. Every single antenna is a door.
Now, the research highlights a specific problem for the security teams tasked with defending these cars. It's called alert fatigue. What exactly is that?
Imagine you are an analyst sitting in a Vehicle Security Operations Center, a VSOC.
Okay.
You are actively monitoring a fleet of 1 million connected cars. You are getting millions of alerts every single day.
Millions.
Millions. GPS signal lost, infotainment system rebooted unexpectedly, door sensor glitch.
That's a constant stream of errors.
Right. And 99.9% of these are just normal software bugs or benign hardware glitches.
But they look like attacks.
They trigger an alert. If you treat every single one of them as a potential Russian hacker, you will never get anything done. You eventually just stop paying attention to the red flashing lights.
It's the boy who cried wolf, but with a million wolves.
That is exactly what alert fatigue is. So how do you spot the real wolf in that noise? The digital twin offers a brilliant solution called contextual awareness.
Uncontextual awareness.
The cyber digital twin doesn't just look at the raw code or the IT network. It looks at the physical state of the car.
Give us an example of how that works. The outline mentions a speed greater than 0 scenario. Walk us through that because it sounds fascinating.
Okay, let's look at a remote unlock command. Let's say a hacker manages to spoof the digital key on your smartphone. They send a malicious command to the car's gateway saying, unlock the trunk.
From the perspective of the code, that looks like a totally valid command, right? The password matches.
Right. A traditional IT firewall might let that through because the cryptographic credentials are technically correct.
So the trunk pops open?
Normally, yes. But the cyber digital twin is watching the state of the vehicle in real time. It sees that the physical vehicle speed is 75 miles per hour.
And you don't open the trunk at 75 miles per hour.
Exactly. The twin knows the physical context. It knows speed is greater than 0. Therefore, a command to open the trunk is physically dangerous and logically inconsistent.
It doesn't make sense in reality.
It flags this as a high-confidence attack immediately. It completely blocks it. It doesn't matter that the password was right, the physics were wrong.
That is brilliant. It's using the fundamental laws of physics as the ultimate firewall.
Exactly.
You can spoof a digital code, but you can't spoof the fact that 2 tons of metal is currently moving down the highway.
That is the power of the cyber-physical model. It fuses the IT world, the information technology, with the OT world, the operational technology.
Are there other examples of this fusion?
Another great example from the research is the kill chain analysis.
The kill chain.
If a hacker enters through the infotainment system, say, you downloaded a malicious music file or an app, and then that malware tries to jump across the network to the CAN bus to control the brakes.
Which would be terrifying.
The digital twin can see that abnormal lateral movement instantly. It says, wait a minute, why is the radio trying to talk to the anti-lock brakes?
The radio has no business talking to the brakes, ever.
Correct. The twin enforces the architecture. It knows the fundamental blueprint of how the car should behave, so it can instantly spot when it's behaving like a compromised machine.
This seems like the only viable way to handle fleet security. You can't rely on human analysts to catch that in real time across millions of vehicles.
No, you need automation, and you need physical context to filter out the false positives. The twin provides both seamlessly.
All right, let's go deeper into the physics side of things. Section 4, the invisible physics.
The black magic.
Exactly. EMC, electromagnetic compatibility. Now, normally when I hear EMC, I just think about the static on my AM radio when I drive under a high-voltage power line. It's a nuisance. But you're saying in these new EVs, it's a critical safety issue.
It is a critical functional and safety issue. Think about what an EV actually is at its core.
Okay.
You have an inverter taking DC battery power and switching it on and off 20,000 times a second to create AC power to drive the motor.
That is a lot of switching.
We are talking about massive currents, hundreds of amps, switching at incredibly high frequencies.
And basic physics tells us that a rapidly changing current creates a magnetic field.
It creates a massive pulsing electromagnetic field. It essentially turns the high voltage cables inside the car into giant antennas broadcasting pure electrical noise.
Wow.
Now wrap those noisy cables around a metal chassis filled with highly sensitive 5G antennas, LiDAR sensors, and millivolt level sensor wires for things like the airbags.
It's like trying to have a whispered conversation at a heavy metal concert inside a shipping container.
That is a very vivid and highly accurate description of the EMC environment in a modern EV.
So what happens if you don't manage it properly?
If you don't manage this noise, the car simply fails. The dashboard screens might flicker or go black when you accelerate hard.
Not ideal.
The radio cuts out when you brake. Or, in a absolute worst-case scenario, the electromagnetic interference could trigger a false positive in a safety sensor. It could deploy an airbag when there's no crash.
That is terrifying. So how does the digital twin fix this invisible floating problem?
We use what the industry calls an executable digital twin, or XDT.
Executable digital twin.
This is where we fuse the 3D CAD data, the physical shape of the metal chassis, the exact routing of the cables, the location of the shielding, with the 2D wiring and electrical topology.
So you combine the physical shape with the electrical logic.
Yes, and then we simulate the electromagnetic field in 3 dimensions.
You can actually see the invisible fog of radiation inside the car model.
We can visualize it perfectly. We can simulate exactly what happens when you slam on the gas pedal. We can see the spike in radiation.
That's amazing.
We can see exactly where that radiation leaks through a tiny gap in the metal shielding and hits the airbag sensor. And crucially, we can do this, here's that phrase again, we can shift left.
Shift left.
Yeah.
That term keeps popping up in the sources. It basically means moving the testing to the left on the project timeline, doing it way earlier in the process.
Yes. We can simulate this electromagnetic storm 6 to 9 months before a physical prototype even exists.
Wow. Because in the old days, what did you do?
In the old days, you built the physical car, turned it on, found out the radio didn't work because of interference, and then you had to tear the car apart to add heavy metal shielding.
Which is expensive.
It is expensive, and it's heavy. Copper and aluminum are heavy, which hurts your EV range. But if you catch the interference in this simulation 6 months earlier, you can just reroute the virtual cable by 2 inches.
Because it costs absolutely nothing to move a virtual cable.
Exactly. And you optimize the weight. You don't just wrap everything in shielding blindly. You only add shielding exactly where the simulation says it's mathematically needed.
But I have to play devil's advocate here. Is the simulation really good enough? Radio waves are notoriously tricky. They bounce, they scatter off everything. Can we actually trust the math over a real-world test?
The accuracy is absolutely stunning. The source material mentions that the error margin between the cloud simulation and the final real-world physical measurement is now within 30 microns.
30 microns. What do you think? That is thinner than a human hair, isn't it?
It is thinner than a human hair. That level of extreme fidelity means engineers can trust the simulation enough to sign off on the design without a physical test.
That is the ultimate threshold for zero prototypes. If the math is that good, you don't need the metal.
Exactly.
That is mind-blowing precision. Okay, we have covered the battery chemistry, the nightmare simulator for the driving AI, the physics-based cybersecurity firewall, and the electromagnetic storm.
We've covered a lot of ground.
It is a massive amount of information, but now we have to talk about how this whole system is actually put together. Section 5 architecture, or as the notes call it, building the brain before the body.
This is the cloud-native development revolution.
The question I asked at the very start of the show, are we designing the brain of the car in the cloud? The answer seems to be a resounding yes.
A completely resounding yes. We are introducing the concept of the VECU, the Virtual Electronic Control Unit.
So an ECU is normally a physical plastic box with a silicon chip inside sitting on a test bench or in the car. You're saying the computer is now just a piece of software running on an Amazon server.
Exactly. It's a virtual machine. But here is the catch. It can't just be any standard virtual machine. This brings us to a critical technical challenge highlighted in the report's bit parity.
Bit parity. Break that down for us. Why is that a challenge?
Well, most cloud servers, the massive data centers running the internet, they use Intel by 86 architecture chips.
Right.
But cars use ARM architecture chips. They are fundamentally different hardware. They speak different binary languages.
So they don't natively understand each other.
Right. If you write and compile your software code for an Intel chip in the cloud, it will not run on the car's ARM chip without a translation layer. And that translation introduces subtle bugs and timing errors.
Which means your test in the cloud isn't perfectly accurate.
Exactly. You can't trust the test. Bit parity means we are now using specialized cloud infrastructure, specifically things like AWS Graviton instances, which use the exact same ARM architecture as the car. We are creating a virtual twin of the car's exact silicon chip in the cloud.
So the software doesn't know the difference. It thinks it's running inside a car driving down the road, but it's actually running in a dark data center in Virginia.
100%. It is identical down to the ones and zeros. This allows massive teams of software engineers to develop, compile, and fully test their code 12 months before the physical silicon chips are even manufactured by the supplier.
That is the time travel aspect of shift left.
Yeah.
You are writing software for a computer that physically does not exist yet.
You are. And think about how this solves massive supply chain issues. Remember the global chip shortage a few years ago?
Oh, yeah, you couldn't buy a car because they were waiting on a $10 chip.
Right. If you have to wait for the physical chip to arrive to start testing your software, your project is dead in the water.
But with the VECU,
With VECUs and strict bit parity, you write and validate the software in parallel with the hardware development. The hardware and software teams are completely unblocked.
this validates the whole shift-left concept completely. You are decoupling the software timeline from the physical hardware timeline.
And that is the only way to move at the speed of the consumer electronics industry. If you want to update your car over the air, just like you update your smartphone, you need to develop it exactly like a smartphone.
Cloud native.
Cloud native from day one.
It's a complete transformation of the workflow. The old waterfall method, do one step, finish it, hand it off to the next guy, that is gone. Everything is happening all at once.
It is simultaneous engineering, entirely enabled by the digital twin.
So we have taken quite the tour today. The battery chemistry, the driver simulation, the hackers, the physics, and the virtual brain.
It's a lot to process.
It really is. But I want to zoom out for a minute as we wrap up. What does all of this mean for the industry at large? If I am a legacy automaker, a Ford, a Toyota, a Volkswagen, how much does this actually change my fundamental business model?
It changes absolutely everything about how you compete. If we synthesize all these battlegrounds, the ultimate takeaway is what we started with. By 2026, the digital twin is the master product.
A master product.
Think about what that means for competitive advantage. For 100 years, car companies competed primarily on manufacturing excellence.
Right. Who makes the best engine?
Who can stamp metal the fastest? Who has the tightest panel gaps? Who has the most reliable transmission? Those things still matter, of course, but they are becoming table stakes.
They are just the minimum requirement to enter the game.
Exactly. The new battle is not being fought on the factory floor. The new competitive advantage will be determined by two things.
And what's the first one?
First, the intelligence level of their digital twins. How good are your mathematical models? Can your battery model actually predict that microshort accurately? Or is it just making a rough guess? The company with the better math wins the safety and efficiency game.
The company with the better math wins. And the second thing?
The speed of their sim-to-real calibration.
Sim to real.
How fast can you take a lesson learned in the simulation? Say, the AI discovers a new, safer way to handle a skid on black ice and deploy that software update to the 5 million physical cars already driving on the road.
The feedback loop.
The feedback loop between the digital twin in the cloud and the physical fleet on the street is the new engine of innovation.
It's not about how fast the car goes from 0 to 60 anymore. It's about how fast the company goes from bug discovered to fix deployed.
Exactly. It is a velocity of innovation contest. And you simply cannot run that race carrying the dead weight of physical prototypes. You have to be virtual first.
It really is a profound paradigm shift. We are moving from a heavy hardware industry that uses a little bit of software to a software industry that just happens to wrap its code in metal and rubber.
That is the absolute reality of the software-defined vehicle.
Well, here is my final thought for you listening at home. We've talked about a lot of invisible, highly abstract tech today. It's easy to lose sight of the physical object. But next time you walk out to your driveway, or you call an Uber, or you slide into the driver's seat of a new rental car, take a second to just look around.
Touch the materials.
Right. Touch the steering wheel, look at the dashboard screens, and remember what we talked about in this deep dive.
What should they keep in mind?
Remember that you aren't just sitting in a dumb machine made of steel, glass, and plastic anymore.
Yeah.
You are sitting inside a physical printout of a massive, incredibly complex digital simulation. The actual soul of that car, its logic, its safety parameters, its personality lives up in the cloud. You are just driving the physical avatar.
Right.
Honestly, that avatar is getting smarter every single day.
That is a perfect way to put it. We are officially entering the age of the avatar.
Thank you for joining us on this deep dive into the digital twin revolution. The brave new world out there on the roads, but at least now we all know what's happening behind the screens.
It was a pleasure to break it down. Drive safe, everyone.
See you next time on the deep dive.